Hello everyone, welcome to Principles of Communication System lecture series. In this lecture video, we are going to discuss about pulse code modulation and line code techniques. Pulse code modulation is one of the modulation technique. In pulse code modulation, a message signal is represented by a sequence of coded pulse, which is accompanied by representing a signal in discrete form in both time and amplitude. In general, pulse code modulation is converts the continuous signals into a discrete signal or digital signals. This signal is suitable for transmission. The pulse code modulation consists of transmitter, communication path, and receiver. The transmitter consists of source, information source. The information source we apply to low pass filter, and output of the low pass filter we connected to sampler, and sampler circuit output again we apply to quantizer, and quantizer output we apply to encoder. So across the encoder we received the pulse code modulated signal. The output of the encoder, so we connected to regenerative repeaters. So this is the regenerative repeaters. So distorted PCM signal is produced at a channel output. So this is the channel output we apply to regenerative repeaters, and again we apply to regenerative repeaters. So this is the regenerated regenerated PCM signal is applied to a receiver. So across the regenerative repeaters, the distortion is very less comparing with the encoder output. So this is the transmission path. The transmission path consists of regenerative repeaters. So output of the regenerated PCM signal we apply to receiver, and receiver PCM receiver consists of regeneration circuit, and regeneration circuit output is applied to decoder. So decoder is the reverse process. The decoder output again we connected to reconstruction filter, and filter output we apply to destination. Now we will discuss in detail about PCM transmitter, PCM transmission path, and PCM receiver. The source information source we apply to low pass filter. The main function of the low pass filter is passes the lower frequency. The output of the low pass filter we apply to sampler. So the main criteria for the sampler is sampling frequency are greater than or equal to 2 omega. So in sampling, the incoming message signal is sampled with a train of narrow rectangular pulses so as to close approximate the instantaneous sampling process. The sampling rate must be greater than 2 omega. The sampling rate or sampling frequency Fs greater than or equal to 2 omega. This is the criteria for sampling. The pre-aliasing filter is used at the front end of the sampler in order to exclude the frequency greater than omega before sampling. The main function of the sampler is converts the continuous signals into samples. So output of the sampler is applied to quantizer. The main function of the quantizer is converts the samples into a digital signals. The quantization process may follow the uniform law as uniform laws we discussed in previous lecture videos. The unacceptable signal to noise ratio for small signal in quantization process. The solution of this is increasing the quantization level. The price is too high. The quantization level it's equal to L. So for example, the quantization level is equal to 7, the noise factor is more. If you increase the quantization level 7 into 18 or 7 into 25, the noise factor will reduces. The main function of the quantizer is converts the number of samples into a digital signals. In certain application, it is preferable to use a variable separation between a representation levels. The use of non-uniform quantizer is equivalent to pass the baseband signal through a compressor and applying the compressor signal to a uniform quantizer. In order to restore the signal samples to their correct relative levels, we must use a device in the receiver with a characteristic complementary to a compressor. Such device is called as a compounder. The compression and compounder law are exactly inverse so that except for the effect of quantization, the expander output is equal to a compression input. The combination of the compressor and an expander is called as a compounder. In PCM modulation technique, the output of the quantizer is applied to encoder. In encoding, the digitalization of analog signal is done by the encoder. It designates each quantized level by a binary code. The sampling done here is the sample and hold process. These three sections, low-pass filter, sampler, and quantizer, will act as a analog to digital converter. Encoding is minimize the bandwidth used. The main function of the encoding process is reduces the required bandwidth. Eh, So coming to line coding, a line code is the code used for data transmission of a digital signal over a transmission line. This process of coding is chosen so as to avoid a overlap and distortion of a signal such as a inter-symbol interference. The main The main properties of the line codings are, as a coding is done to make a more bits transmit on a single signal, the bandwidth used is much reduced. For a given bandwidth, the power is efficiently used. The probability of the error is much reduced. The error detection is done and the bipolar 2 as a correction capability. The power density is much favorable. The timing content is adequate. The long string of ones and zeros is avoid the main transparency. These are the main properties of the line coding techniques. The line coding mainly classified into three types. The first one is unipolar line coding technique, and second one is polar line coding, and third one is bipolar line coding. Let's consider unipolar line coding or signaling. In unipolar signaling is also called as a on-off keying or simply OK. The presence of pulse is represent a 1 and absence of pulse is represent a 0. So in unipolar signaling, there are two variants in unipolar signaling. The first one is non-return to 0 and second one is return to 0. In unipolar signaling, so 1 is represented as a on and 0 is represented as a absent or off. So let's consider unipolar non-return to 0 signaling. So in this type of unipolar signaling, a I data is represented by a positive pulse is called a mark, which has a duration T0 is equal to any symbol bit duration. A low is low data input as no pulses. The following figure is clearly depicts this. So let's consider 1010011110. So this is the given data. So we have to convert this digital data into a line coding by using unipolar non-return to 0 technique. So this is the 0, this is the 0 line or reference line, and this is the positive voltage level V. So in unipolar non-return to 0 technique, 1 is 1, it's equal to positive value, positive voltage level, and 0 is equal to reference. 0 is equal to reference value. So this is the marked line. Then you join this axis, and again second bit is equal to 0. So 0 is equal to reference, and next bit is equal to 1. 1 it's equal to positive voltage level. 0 is equal to, you retain as it is, and again 0, this is the 0 line, and next bit is 1. So this is the IR value or positive value, and next bit is 1 and mark here, and next bit is IR value 1. 1 is equal to positive voltage level, and next bit is 0. So 0 it's equal to reference value. So this is the conversion. In unipolar non-return to zero technique, 1 is equal to positive value and 0 is equal to 0 level. So this is the line code for the given digital data. Let's consider unipolar return to zero line coding technique. In this type of unipolar signaling, a I data through represented by a mark pulse, its duration T0 is less than the symbol bit duration. Half of the bit duration is remains I. Half of the bit duration is remains I, but it's immediately returned to 0 and show the absence of pulse during the remaining half of the bit duration. So let's consider 1 0 1 0 0 1 1 1 0, and this is the given sequence or given digital data. We have to convert this given data into line coding by using unipolar return to zero techniques. In unipolar return to zero technique, this is the I value. So I value, for example, this is the bit duration T0. So here given input is 1. So half of the bit duration from here to here, this is the full duration and this is the half of the duration. So given input is 1, half of the bit duration is I. After that, it's immediately is returned to 0. So next bit is 0, you return as it is 0, and next bit is 1. So half of the bit duration is I, and immediately is returned to 0. So this is the representation. Next bit is 0, you return as it is, and next bit is 0, and next bit is 1. So half of the bit duration is positive voltage level, and another half of the duration is returned to 0. And again next bit is 1, half of the bit duration is I, and another half is returned to 0, and next bit is 1 and half of the bit duration is returned to 0, and next bit is 0, you return as it is. So this is the line coding signal. In unipolar line coding, 1 it's half of the, if in case of 1 is the digital data, half of the bit duration is I, another half is returned to 0. The input bit is 0, you retain as it is. Let's consider polar signaling. In polar signaling, we consider both positive and negative voltage level. So this is the reference line. So reference line is equal to 0, and this is the positive level, and this is the negative level. So in unipolar, we consider only positive level. So in polar, we have to consider positive voltage level as well as negative voltage level. So 1 is the input data. So 1 we consider as a positive voltage level, and 0 we consider as a negative voltage level. So in polar signaling, there are two methods of polar signaling. They are polar non-return to 0 and polar return to 0. Let's consider polar non-return to 0 line coding technique. In this type of polar signaling, a I data is represented by a positive pulse, while a low data is represented by a negative pulse. The following figure is depicts this well. So let's consider 1010011110. This is the given digital data. So in polar signaling, 1 it's equal to positive voltage level and 0 it's equal to negative voltage level. So this is the reference line. This is the reference line 0. The first bit is 1. 1 it's equal to positive voltage level and next bit is 0. 0 it's equal to negative voltage level and again next bit is 1. So 1 is equal to positive voltage level and 0 is equal to negative voltage level. Similarly next bit is 0. 0 is equal to negative voltage level and next bits are 1 1 1. It's equal to positive voltage level and next bit is 0. So this is the line code representation. So in polar signaling, so 1 it's equal to positive voltage level and 0 it's equal to negative voltage level. So let's consider polar return to zero line coding technique. In this type of polar signaling, a I data through represented mark pulse, its duration T0 is less than the symbol bit duration. Half of the bit duration remains I, but it's immediately is returned to 0 and it shows absence of pulse during remaining half of the bit duration. However, the low input, a negative pulse represents the data and the 0 level remains the same for the other half of the bit duration. The following figure depicts this clearly. So let's consider 1010011110. This is the given digital data. We have to convert this digital data or values into a lines by using polar return to 0. So we know that in return to 0, half of the bit duration is I, whether it's a higher value or lower value. So another half of the bit duration is returned to 0 value. So in polar signaling, 1 it's equal to positive value and 0 it's equal to negative value. So this is the reference line. This is the reference line and this is the positive voltage level and this is the negative voltage level. So we have to convert given data into a line coding signal by using polar return to 0 technique. So the input is 1. So 1 it's equal to positive voltage level. So in return to 0 technique, half of the bit duration is higher value and another half is returned to 0. The next bit is 0. The 0 is equal to negative voltage. Half of the bit duration is negative voltage level and another half is returned to 0. And next bit is 1. Half of the bit duration is higher value and another half returned to 0. Next bits are 0 0. Half of the bit duration is negative voltage level and another half is returned to 0. And next bit is 0. Half of the bit duration is negative voltage level and another half is returned to 0. And next bits are 1 1 1. So half of the bit durations are I and another half is returned to 0. Half of the bit duration is positive voltage level and another half is returned to 0. And half of the bit duration is positive voltage level and another half is returned to 0. And next bit is 0. So half of the bit duration is negative voltage level and another half is returned to 0. So in polar return to 0, 1 is the input, the half of the bit duration is positive voltage level and another half is returned to 0. The input is 0, half of the bit duration is negative voltage level and another half is returned to 0. So this type of coding technique we called as a polar return to 0 line coding techniques. Bipolar signaling is one of the line coding technique. In this is an encoding technique which has a three voltage levels, namely positive, negative and 0. Such a signal is called a duo binary signals. An example of this type is alternate mark inversion AMI. For an 1, the voltage levels get transition from positive to negative or from negative to positive, having a alternate ones to be equal polarity. A 0 will have a 0, 0 will have a 0 voltage level. Even in this method, we have two types. The first one is bipolar non-return to 0 and second one is bipolar return to 0. From the models so far discussed, we have learned the difference between non-return to 0 and return to 0. In non-return to 0, so voltage levels are positive level or negative cycles, total bit duration. In return to 0, half of the bit duration is higher voltage level or lower voltage level and another half is return to 0. It just goes in the same way here too. The following figure is clearly depicted this. So let's consider 1010011110. This is the given binary data. We have to convert this data into a signaling or line coding by using bipolar non-return to 0 techniques. So here in bipolar signaling we consider only IR value 1, 1, 1, 1 and 1. So 0 we 0 levels we retain as it is. So this is the reference line, this is the reference line and this is a 0 and this is positive voltage level and this is the negative voltage level. So this is the 1 is the higher value. So first one is the higher voltage value and second one is the lower voltage level or negative voltage level and next one is positive voltage level and next higher value is negative and next one is positive. So bipolar signaling is a alternate mask inversion AMI techniques. So here the first bit is 1. So first bit is 1. So 1 it's equal to positive voltage level and next bit is 0. You retain as it is 0 level and next bit is 1. The previous one is positive voltage level. Next one is transition, the positive to negative. The voltage level, this is the voltage level and next bit is 0. You retain as it is and next bit is 0 and next bit is 1. The previous one voltage level is negative and next this voltage level is positive, is transition from negative to positive. So this is the voltage level. The next bit is 1. The previous value is 1, the voltage level is positive and this one is negative, it's transition from positive to negative. So this is the voltage level and next one is positive voltage level, it transition from negative to positive and next bit is 0. You retain as it is. So this type of transition, this type of conversion we called as a bipolar non-return to 0 techniques. So coming to bipolar return to 0. So this is the given input signal. So in bipolar signaling we consider only higher value 1, 1, 1, 1 and 1. So this is the return to 0. So let assume the first one is positive voltage level and next higher value is negative and next one is positive and next higher value is negative and next one is positive. So in return to 0 technique, so half of the bit duration is higher positive voltage level or negative voltage level and another half is immediately is returned to 0. So for example, this is the first bit. The first bit voltage level is positive, half of the bit duration is positive and another half is returned to 0 and next bit is 0. You retain as it is and next bit is 1, 1 and 1 is the negative voltage level. This is the bipolar signaling technique. So this is the negative voltage level. Half of the bit duration is negative voltage level and another half is returned to 0. Next bits are 0, 0 written as it is 0 levels, and next bit is 1, the voltage level is positive. The previous n is negative, is transition from negative to positive. So half of the bit duration is higher voltage level and another half is returned to 0. The next bit is 1, the level is negative voltage level and another half is returned to 0. Next bit is 1, the level voltage level is positive voltage level, half of the bit duration is positive voltage level and another half is returned to 0. Next bit is 0, written as it is. So this type of conversion, this type of digital to line coding conversions we called as a bipolar return to 0. Manchester encoding is one of the line coding technique. The Manchester encoding translates a 1 into a low to high, 1 into a low to high transition 0 1, and 0 is translated into a high to low, also called a biphase code used with a Ethernet interface. Let's consider one specific example. So 1010011110001 is the given digital data. We have to convert this data into a line 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 coding by using Manchester encoding technique. So we know that, so in Manchester encoding 1 is transition from low to high and 0 is transition from high to low. So the first bit is 1. So 1 is transition 1 is transition from low to high. So this is the bit duration of the 1 from year to year. Half of the bit duration is low and another half is returned to high. And next bit is 0. The initial half of the bit duration is high and another half is returned to 0, and next bit is 1. So half of the bit duration is negative level and another half is returned to high. The next bits are 0 0. Half of the bit duration is high and another half is returned to 0, and next bit is 0. Half of the bit duration is 0 and another half is returned to 0. So next bits are 1 1 1. So 1 is the bit value, it's initially it's negative voltage level and 50%, another 50% is positive voltage level. So similarly the next bit is 1, so half of the bit duration is negative voltage level and another half is positive voltage level, and next bit is 1, half of the bit duration is negative voltage level and another half is positive voltage level. Next bits are 0 0. So bit input bit is 0, the half of the bit duration is positive voltage level and another half is returned to 0. The next bit is 0, the half of the bit duration is positive voltage level and another half is returned to 0, and next bit is 1, half of the bit duration is negative voltage level and another half is returned to positive voltage level. So this type of conversion or this type of line coding we called as a Manchester encoding techniques. Differential encoding is one of the line coding techniques. In this method is used to encode the information in terms of signal transitions. The transition is used to designate a symbol 0 in the incoming binary data stream, while no transition is used to designate the symbol 1. The waveform of the differential encoded data assume the use of the unipolar non-return to 0 signalings. The original binary information is recorded by comparing the polarity of the adjacent binary symbols to establish whether or not a transition has occurred. Notice that differential encoding requires the reference bit. It requires the reference bit before initial process. Let's consider one specific example. So the original binary data are 0 1 1 0 1 0 0 1. This is the original binary data. So in differential encoding technique, so initially we need one reference line, whether it's a higher value or lower value. So usually we assume higher values. The reference bit is 1. So reference bit and given digital input bit we apply to XNOR gate. So 0 and 1 we connected applied to XNOR gate. So 0 is the 1 bit and 1 is the reference bit we applied to XNOR gate. The 1 and 0 we applied to XNOR gate, resulting value is 0. And again, next bit is 0 and 1 we applied to XNOR gate, resulting value is 0. Next bit is 0 and 1, the resulting value is 0. Next bits are 0 and 0 we applied to XNOR gate, resulting value is 1. And again 1 and 1 we applied to XNOR gate and resulting value is 1. Next bit is 1 and 0, the resulting value is 0. Next bits are 0 and 0, resulting value is 1. And next bit is 1 and 1, resulting value is 1. So this is the differential encoded data. The differential encoded data are 1 0 0 0 1 1 0 1 1. So 1 is the reference bit. So in differential encoding is the unipolar non-return to 0 signaling. So in non-return to 0 signaling, so this is the reference line, 1 is equal to higher bit. So this is the reference bit, 1 is the reference bit, next bit is 0 0 and next bit is 0 0 is equal to 0 level and next bit is 0 and 1 is equal to positive voltage level, and this is non-return to 0 technique. And next bit is 1 and next bit is 0. So this is a 0, next bits are 1 and 1, this is 1 and 1. So this type of conversion or coding, line coding, we called as a differential encoding. Let's consider one example. The given binary data are 0 1 1 0 1 0 0 1. We have to convert given digital data into a different line coding techniques. The first conversion is the unipolar non-return to 0. This is the unipolar non-return to 0, NRZ technique. The next one is polar return to non-return to 0, and next conversion is unipolar return to 0, and fourth one is bipolar non-return to 0, and this one is Manchester, and last one is differential encoding. So this is the given data. The first we have to convert given data into unipolar non-return to 0 line coding format. So here 0 is you retain as it is, and 1 is the higher value, higher voltage level, and again 1 is the higher voltage level. Next bit is 0 0 is the 0 level, and next bit is 1, and next two bits are 0 0 and next bit is 1. And next conversion is polar non-return to 0. The given first bit is 0 0 is the negative voltage level, and next bits are 1 and 1, next bit is 0, next bit is 1, and next two bits are 1 1 and next bit is 1. The next conversion is unipolar return to 0. In unipolar return to 0, so in unipolar 0 we return as it is, 1 the half of the bit duration is positive voltage level and another half is returned to 0. The next bit is 1, half of the bit duration is higher value and another half is returned to 0. The next bit is 0, 0 you return as it is, and next bit is 1, half of the bit duration is positive voltage level, next bit is 0. Next two bits are 0 0 you return as it is, and last bit is 1, the half of the bit duration is positive voltage level and next is 0. Next and half of the bit duration is positive voltage level, immediately is returned to 0. And next conversion is bipolar non-return to 0. In bipolar non-return to 0 we consider only higher value 1 1 1 and 1. Let's assume the first bit is first IR value is positive voltage level, next is negative, next bit is positive, and next is negative. So here the 0 you retain as it is, 0 is a 0 voltage level, and first one is positive level and next one is negative level, and next bit is 0 you retain as it is, and next bit is positive voltage level, and next two bits are 0 0 you retain as it is, next bit is negative voltage level. So this is a negative voltage level. And next conversion is Manchester. So in Manchester conversion, 0 is the input. It varies from positive to the next conversion is Manchester encoding. So in Manchester encoding, so 0 in this particular example, 0 varies from negative to positive and 1 varies from positive to negative. So for example, if you take 0, it varies from negative to positive, 1 it varies from positive to negative. So this is the one method. The another transition is 0, it varies from positive to negative, 1 it varies from negative to positive. So in previous example we use this method, and this particular example we use 0 it varies from negative to positive and 1 is varies from positive to negative. So here first bit is 0, it varies from negative to positive, and 1 is varies from positive to negative. So similarly for next bits, so 1 varies from positive to negative and 0 varies from negative to positive and 1 varies from positive to negative. So similarly for last bit, so last bit is 1 varies from positive to negative. And last conversion is differential encoding. So in differential encoding we need reference bit. So here reference bit is IR value 1. So 1 and 0 we apply to XNOR gate, resulting value is 0, and again next bit is 0, next bit is 0, next value is 1, and next two values are IR value, and next bit is 0, next two bits are 1 1. In PCM modulation technique, the encoded signal we connected to transmission path. So transmission path consists of regenerative repeaters. The most important feature of any digital system lies in the ability to control the effect of distortion and noise produced by the transmitting a digital signal through a channel. The main function of the regenerative repeaters is to reduce the distortion. This capability of accomplished by reconstructing the signal by means the chain of regenerative repeaters which perform the three basic functions: equalization, timing, and decision making. The regenerative repeaters consists of amplifier, equalizer, decision making device, decision making, and time circuit. So distorted PCM wave we apply to amplifier equalizer. The output of the amplifier equalizer we apply to decision making device, and same output again we apply to time circuit. The output of the time circuit again we are connected to decision making. So across the decision making device, so we received the undistorted or less distorted regenerated PCM wave. So equalizer is shapes the received pulses so as to compensate for the life effect of the amplitude and phase distortion produced by the channel. This is the function of the equalizer. The timing circuit provides the periodic pulses strain derived from the received pulses for sampling and equalized pulses at the instant of time where the signal to noise ratio is a maximum. So this is the function of the timing circuitry. The decision making device, the function of the decision making device is sample extended is compared to a predetermined thresholds. The regenerated signal may depart from the original signal. The unavoidable presence of the channel noise and interference causes the repeaters to make a wrong decision occasionally, thereby introduce a bit error into a regenerated signal. If the spacing between the received pulses deviates from its assigned value, a jitter is introduced into a regenerated pulse position, thereby causing the distortions. The undistorted signal is applied to PCM receiver. The PCM receiver, it consists of regeneration circuit, decoder, reconstruction filter and destination. So this is the PCM receiver block diagram. The first operation in the receiver is to regenerate the received pulses one last time. These clean pulses are then regrouped into a code words and decoded into a quantized PAM signal, pulse amplitude modulated signal. The decoding process involves with generating a pulse, the amplitude of which is linear sum of all the pulses in the code word, with each pulse being weighted. Its place value is 2 to the power 0, 2 to the power 1 to 2 to the power r minus 1, where r is the number of bits per samples. The final stage is filtering. The final operation in the receiver is to recover the message signals wave by passing the decoder output through a low-pass reconstruction filter whose cutoff frequency is equal to message bandwidth W. So these are some references. Thank you.